Huh? Oh, well, there's me giving a monologue to no one. Anyways, shout out to my roommate for this new keyboard. He hooked me up with it. He got a new one. Nice mechanical keys. So that's both satisfying and obnoxious, and I look forward to doing my thing on it. Anyways, welcome to Bayesian Cognitive Modeling, where I go through all of the exercises in Michael Lee and Eric Wagenmakers' book on using Bayesian inference in order to understand cognitive sciences or understand research questions within the cognitive sciences or experimental paradigms commonly used within the cognitive sciences. And so we want to be able to take full advantage, take full advantage of the all of the modeling possibilities that we could potentially use in order to understand cognitive processes, some of which are done using Bayesian techniques, and that's the main focus of what we do here. So, welcome. Last time, we finished up the hierarchical model for the risky decision making paradigm, where we were looking at the BART, which is a behavioral task that attempts to make assessments about individuals' risk sensitivity. And we looked at, or risk seeking, or risk taking, I guess. Some people just call it under various names. I'm used to calling it the name that I conceptualize it as, though this particular measurement is trying to capture risk preferences towards scenarios that involve taking on some potential harm or hazard, if you will. Mm-hmm. So trading off the hazard for some potential opportunity for gain. And so we did that, and we looked at how we could model the BART using a cognitive model shown here. Or I don't have the graphical model pulled up, actually. Oops. Oh. Uh-oh. Here we go. Oh no, I don't want to combine files. I just want to pull up the cognitive model. Here. And then we looked at extending this model in order to account for effects across conditions. In this case, we were looking at still within a single individual, how we could model changes in behavioral consistency and risk taking as a function of intoxication. And we found varying results across two individuals. And then one of the last questions asked if we could extend this model to account for effects across individuals within the same model. And the answer is, well, yes, it's just a lot bigger. So it's just one more additional plate. I actually went ahead and drew out a little sketch schematic of what it would look like here. And basically the conclusion I came to is it would just be adding another cluster, like another level to the hierarchy here. So if you wanted more information about that, go check out yesterday's stream. Although I will say yesterday's stream was a little wonky because I was having challenges with my CPU. I'm still not sure about what that was all about. I think it has something to do with a program I ran earlier that day, which basically devoured my memory. And that was all it too. I still had that open. I think that's what it was. But today we're going to start chapter 17 here of, I believe, 19 chapters. So we're coming to the end here, which is really exciting. Yeah, so we're going to finish basically just on time, if I'm not mistaken. Because this is also the last week I'm going to be streaming, or at least streaming for the Bayesian Cognitive Modeling practical course book. In the future, I'd hope to do explicitly maybe code up or edit some videos where I talk about how to do simple data analysis procedures, or talk about particular packages and the advantages of using said package, and then do some demonstrations and attach some code along with that. That seems to be, or those sorts of videos have been really helpful for me personally, and I would love to see that sort of, do that sort of procedure. Although I could also, do some more of this, speak aloud, live stream sort of thing with a different textbook. I just got a new book I'm really excited about. I guess I can show you if you want. Regression and Other Stories. It's got Gellman as one of the authors. Andrew Gellman, who's really big, statistician, and quite a big in the realm of Bayesian statistics. And he recently released this new textbook talking about, well, it's really just a book focused on using regression in order to answer problems. However, the book also introduces Bayesian analysis, and it's aimed at a textbook for, well, it could be used for undergraduates. So it's really exciting to see how can we incorporate things like data simulation and Bayesian analysis into an undergraduate curriculum, potentially using a book like this. So I look forward to making my way through this material and seeing how they talk about it. They do it on R. It's going to be cool. That's it. So maybe I'll do something with this. It's a little thicker, and it won't be like one of these month challenges things like this, but I'll definitely be on hiatus for a second, because in May I need to double down and finish some things for my research here at my university, and then I also have class stuff. So that's what we'll be focusing on then, but this has been a bunch of fun. So let's get right into it then. Okay. So here today we're looking at the generalized context model. So it's I'm just gonna read along with you guys here. So it's a model of categorization. Well, what do we mean by categorization here? So it's intended to explain how people make categorization decisions in a task where the stimuli are presented one at a time over some sequence of trials, and then people are tasked with classifying this set of items into some small number of categories, and commonly we use just 2 categories, but it could be several categories, and they get feedback along the way. So there is some potential learning that could be explicitly modeled here as well, it looks like. So generalized context model, okay. Assumes, so what are some of the assumptions that we're making here, or theoretical assumptions, so it seems? Well, the generalized context model assumes that stimuli are stored as these exemplars, and using their values along with some underlying stimulus dimensions, so some attributes. Let's delete this. Okay. The context model assumes people make similarity comparisons between the current stimulus and some exemplar based on their decisions of overall similarities in each category. Okay, so each of the categories, there's some sort of exemplar, and across the span of trials, people are in reference or assessing some set of attributes about each of the particular stimuli and seeing which of the exemplars that they have in mind does it best match to, and then that's what the particular stimuli gets classified as, it seems. Okay. Points in a multidimensional psychological space. Okay. Key theoretical component involves selective attention. And what do we mean by that? Okay. So the basic idea there is people are attending to dimensions of stimuli that are most relevant to distinguishing categories. So whichever category they have in mind, say it was pet or animal, then they would be selectively attending to the dimensions that help them make those distinctions between the categories or stimuli. Kirchhoff? Are we talking about the same Kirchhoff here? Kirchhoff in 1993. I think we are. Yeah, the Kirchhoff that we're talking about here is the same Kirchhoff that wrote the dog book, I think. J.K. Kirchhoff, yeah. Well, that's cool. So he's been in it for a while, because that's 1993 publication means you had to be 1990. You had to be old enough to publish by 1993. Okay. We consider category learning data from condensation B condition, reported by Kirchhoff, 1993. This is a category learning experiment involving corrective feedback after every trial. Usually generalized context modeling is not applied to this sort of task, but to categorization decisions made without feedback after a training period. Okay. The condition is shown in 17.1. Here's 17.1. Condensation category structure B. Kirchhoff stimuli above diagonal belong to category B, and stimuli below diagonal belong to category A. It involves 8 stimuli consisting of line drawings of boxes with different heights. So the boxes have different heights, okay. With an interior line in a different position. And we're divided into 2 groups of 4. So we have varying heights of the boxes and then varying positions of the lines. Okay. Category A and B stimuli. Kirchhoff collected 40 participants 8 consecutive blocks. Within each stimulus was presented once in random order. The data can be summarized by YIK, which is a given individual for a condition, I think. So let's see. The number of times the ith stimulus was categorized as belonging to the category A by the kth participant. I see. So it's a binary. So, there's a Poisson. Let's see, the number of times the stimuli was categorized to A for a given participant. So some count. So some count for a given stimuli for a given subject out of the T trials. In the analysis that does not consider individual differences, the data can be summarized as some sum of the count of the subjects of all the counts of these. So we just sum across the subjects, right? So we end up with counts for each of the items that are put in the category A out of a total number of presentations given by 40 trials per 8 blocks. Okay, that makes sense. So we have a graphical model of the representation in 17.2. And before I read this, let me take a look and we'll make some guesses about the graphical model here. So here it is, the generalized context model for categorization. And we have tons of parameters. So let's see. I see some J's, I's. I see Y. So we're not looking at individual differences here. We're just looking at the group. So here's the count of category A for a given stimuli. T is some other discrete variable. T is the block number, right? Or is the total amount of trials. So 40 times 8 here, right? I think it said that way above. Yeah. And then we have R, which is derived from this formula, which is made up of some continuous variable B, which I have access to, which I think is if it's 1/2, I'm going to guess that represents either category A or B, right? And then A here is another discrete variable that's not represented. And then we have IJ pairs of stimuli. And we have these parameters for that. So P, some constant P. WC priors. Difference. I don't know what M is yet, but the absolute difference between some item M and some item. We have the difference between them represented here. So the difference between the pairs. That helps us give us S, which is this. So for S for a given pair, and S looks like it's important. All right, let's learn what they are. Okay, so 2 stimuli, ice and there are 2 stimuli dimensions. So the ith stimulus is represented by the point P, I, 1 and 2. The first dimension has a tension weight D. Second dimension has a tension weight 1 minus whatever the other weight is. Okay, so that makes up the total sum of the weight is equal to 1 with if one dimension gets weight, then the other dimension. So each particular stimuli varies as a function of height and line position. And so individuals are putting weight, selectively attending to one of these two dimensions for a given stimuli. And this weight then represents which of the two, well, first it represents which of the stimuli the individual is attending to more heavily. Okay. So these weights act to stretch attended dimensions and to shrink unattended ones. So the psychological distance between two stimuli is represented by whatever this weight is. So we're adjusting the weight. We're weighing the difference by the weighing of the two stimuli. So P for stimulus pair 1 here, for example, looking at height, this would be the difference between the two heights scaled to the weight that the people are attending to this. So the total difference is going to be the sum between these two things, accounting for the weighting of attention to that given dimension. Cool. The similarity between the ith and j stimuli. So if they're similar to one another, so this accounts for similarity. So we have similarity, attention weight. Where C is a generalization parameter, okay? C is generalization parameter. The overall similarity between stimuli when it is presented to category A is that. It's the sum of all the pair J. Sum of the similarities. The graphical model uses an unbiased choice rule so that the probability that the ith stimuli classified as belonging to category A rather than category B is here. Unbiased choice rule represented by R. So what's A? I still don't know what A is. Okay, so we start at 50-50. This is going to represent the choice rule for a given item, which is going to be controlling the probability of choosing A for a given item with this count. So we care about this. We have some constant, we have the decision weights, W, S, decision weight W, and then we have the difference between the points for the two differences between the points for the two attributes or dimensions. In this case, 2 dimensions. So let's open it up. We are going to set our working directory here. Oh, I'm in Stan. That's weird. I don't know if I want to use the Stan code. Well, I have the Stan code here. I will not be using the Stan code just yet. I want to look at the JAGS code. Books. Doesn't look like you can execute the generalized context model in R. It's so weird. I'm looking if I can find the code. Alright, it doesn't look like this executes in JAGS. Here's the Stan code. Let's talk about it. So for each of the stimuli, we model Y as binomially distributed with R, where R is for each item. We have T across the sample. And then preddy Y is for, I believe it's a predictive. Note that it collects the posterior predictive samples for the decision data in preddy Y. Or pred Y, whatever, I'm saying preddy Y. So it's a binomial distribution again, so this is going to be the predictions. So now we set up the decision probabilities here. So for each of the stimuli, let R be equal to here, sum of numerator, denominator. And then we have to define what the numerator and denominator are. Well, numerator here, ij, is going to be equal to temp1 ija, and denominator is temp1 ija plus temp 2, IJA. Well, what are temp 1 and temp 2? Or they are just these things that we set. And create some array here where for the pair, for the first pair, is equal to B, SI, which you specify S below. It's a similarity coefficient. And then temp 1, 2 is equal to nothing. Temp 2, 1 is equal to nothing. So this, I guess we do this so we can take advantage of using the array structure here, but then, when we do so, there's two categories that don't make sense. We have to do the similarities between the stimuli, so we do the nested for loop again, and we estimate the formula here, and then we set these priors. Cool. Now we're going to look at the arc stand code, since it looks like that's what we can execute. I'm going to try to execute it here. Oh, you mad? Eight stimuli, so 8 blocks of trials. The probability, or the counts for choosing A across the blocks here for stimuli pairs. We see across the stimuli, it looks like there are 3 stimuli who are particularly or discriminability of 6 of the stimuli are quite high, where it's easy to say that these 3, whatever they are part of A, and the bottom 3 are part of B, though for stimuli 4 and 5 it's not really clear, and so we have this sort of, it might be over here, over there. They're closer to one another, I guess is the point I want to make. And here we have the attention weight, which for W, which we have generalization. I'm not sure what generalization is. We can take a look here. The plot, XLab, C. So that's C. Let's take a look at the samples. C here, average C. And why did we follow C as the parameter? C represents, where C is a generalization parameter. I don't know what that means. Well, how do we code up C? 0 to 5. Okay. Let's see what the... I see why we do pretty Y now, so we can get these outputs. Quick. Look at the variability around those now. Because they added the second chain. Okay. Let's see. Okay, so the joint posterior between the generalization parameter C and the tension weight parameter is the scatter plot. The key result in terms of theory of category learning and selective attention is that the attention term W lies between here. This can be interpreted as people give significant attention to both dimensions, although they probably focus a little more on the line than on the rectangle height. So because it's near 0.05, people are giving a lot of weight to both dimensions, but it looks like there's a little bias towards giving one dimension a weight, than more weight than the other. Why do we model this like this with the generalization parameter? This is consistent with the condensation task designed for category structure. It is clear. It is clear from 17.1 that both dimensions are relevant in determining which category a stimulus belongs, so a shared attention result makes sense. You're looking at both. Oh, I see. So what were the hardest stimuli then? It says 4 and 5. 4 and 5. But even so, it wasn't that hard. It looks like 4. So 4, 6, 8, and 7. 4, 6, 8, 7 are all lower, category B. And then we have 1, 2, 3, 5, 1, 2, 3, and 5. Right? Okay. How did we know that this higher value it dealt with the line position? Yeah, but it's still, if you look at the credible interval, it's pretty 50-50. People are paying attention to both. And this is the predictions across each item in terms of the counts for being in each of the categories. Where 4 was the highest miscategorization here. Because we'd expect a lower value for that particular one. And there's far more variability surrounding those estimates. Looks like a lot of variability. All those. Put the count here. Yeah, but they don't overlap. So that's fine. Yeah, they don't really overlap. I think these are the predictions underneath, right? Yeah, we're just counting the predictions. And then we add a line. Neat. Okay. Setting beta or the choice prior to 0.05 to make the decision rule unbiased seems reasonable, since there are 2 alternatives with equal number of equally often presented stimuli, but the assumption can be easily examined. Change the model so that the bias parameter b is given a uniform prior over the range of 0 to 1 and is inferred from the data. Okay. So I'm going to watch B now, and then I have to initialize B, and I'll initialize at 0.5, right? Last thing to do then is to add B here. Zero to one. So all I did was tell it I want to watch B. I initialized some values for B. And then I added a prior distribution uniform from the range 0, 1 here. And then in the parameters, I specified that B here. And then I don't have to change anything here for the transformations. So that's nice. So let's take a look. First, let's take a look at how does it change any of the plots. Doesn't look like it. B ends up being right around 50% anyway. All right. So when we infer what B is from the data, instead of just specifying it as being equal to 0.5, we get the same result. At least when I run 2 chains. Okay. Now, let's see. Figure 17.4 shows a posterior predictive analysis of the modeling. Oh, make sure the difference. Yeah, decision weight is still the same. Okay. Overlaid on the gray violin plots showing the posterior predictive distributions. Here, posterior predictive distributions sort of looks like our plot. Our plots. It's these lines. Also shown by the broken lines are individual participants. Okay, subjects. So variability here in terms of ability to classify. These are linearly scaled from the individual counts of 8 to the group counts of 320 to allow visual comparison for the number of times. I would say that the group data, I mean, we adequately are predicting the group performance. However, on a scale of an individual, there's substantial variability in terms of what someone's category decision was for a given stimuli. So some people are just better at categorizing than others. So it looks like. And like what we referenced beforehand when we were looking at this image above, these predictions correspond pretty nicely with these the stimuli. Although, as we already specified, stimuli 4, it seems, is less discriminable than the other stimuli. And we say that because of the sheer counts of whether it was categorized as A and tend to be higher than what we'd expect of for it being a part of category B. And why might that be the case? Well, let's take a look at stimuli 4 here. Stimuli 4 kind of looks like 2, maybe. I don't know. It also has positioning similar to 3. I guess it could be considered a tougher one. Okay. So figure 17.4, right, as I mentioned, suggests substantial individual differences in people's categorization abilities, with people categorizing things differently than what we'd expect given the actual real category the stimulus belonged to, as was shown above. And here's the category data for all 40 subjects. So this is just taking these dotted lines that are underlying this graph here and just putting each of them in their own box. This guy. Simplest way to start investigate these differences is using the generalized context model would be to just infer parameters for each subject. So we have weights. We'll have weights, generalization, and bias for the choice or unbiased choice inferred for each subject. And then, right, it's just slapping more I's on everything, right? Or slapping K's on stuff. So then we're going to have an R for each subject. We'll have the counts for each subject instead of the aggregated counts. And nothing about the formalization here in terms of the how we derive these parameters or determine these parameters changes. It's just adding additional subscripts where necessary. For example, the stimulus differences don't change as a function of subject, but the similarity does. So we still get these differences derived between two pairs, but then the weighting given to them by the generalization and the weight parameter has subject-specific values, which then feed into this R, which tells us the rate for the counts. Okay. So that's the extension. And we're going to go over to the JAGS code, the stand code now. We've just been doing stands code because something about the code derived or in the file on the website for the book doesn't have JAGS code in it or JAGS scripts, and wonder why that is the case. Looks like we set B for everyone again. Everyone gets 0.5. But as we saw from the last example, when we inferred that, it didn't change the model. GCM-2R. GCM-2R doesn't exist. So I don't know what you're talking about. So simple enough. Let's run it. While that runs, I'll clean up some of the code. It sure is cooking. It's surfing that sweet distribution NAR. It's an interesting choice of plot. Maybe I should clear the plot history and then try again. No warnings this time. So we're going to get C's for each of the subjects. And you can see there's substantial variability in the C's. And then weights. So some subjects attend to some stimuli while others attend to other stimuli. Some people look at the lines, some people look at the heights. And here are the predictions for each of the items pairs. Right? Oh, here's the predictions for each of the items for each of the subjects. Sorry. Oh, I see. We didn't print them all. And then let's get the plot. Very interesting plot. What is this plot supposed to look like? There we go. Where was this? So now we have attention weight and generalization again. But this time we have each subjects. We have the errors associated with it. It's weird U phenomena happening here. W, generalization parameter C. More constrained models of variation in category learning. I see. So from this, I was overstepping my bounds. But latent, that's the next thing. We're going to do that tomorrow. It looks like it's getting really late. I took too late. Right, compare the inferences about the attention parameter based on the individual subject analysis with those based on a no individual analysis. Right, so like I said before, it looks like some individuals selectively attend to the weights, while some individuals are selectively attending to the lines. So instead of attending to one or the other, as in these subjects here, we have subjects who are biased towards attending to one stimuli above and beyond the other. Like these particular, like 33, for example, attending essentially only to the lines or the heights, while 3 is attending heavily to the lines and demonstrating that people there's variability in terms of the attending to stimuli. And it looks like there might be some groupings here, which is what we're going to talk about, like how we can potentially predict these latent groups using concepts that we talked about early on when we were doing latent mixture models. So 3 of the individual subjects' joint posteriors are labeled. These 3 subjects lie in different areas of the parameter space and so possibly correspond to different sorts of categorization behavior. Okay. So let's take a look. So 3, 31, and 33. The best way to do this, look at this plot. 3 here. It looks like 3 chose stimuli, had a hard time with these, and then chose these. And then we're supposed to look at 31, 33. 31, 31 score. Interesting. 31's here, where it looks like their attention weight .31's attention weight here is quite variable. So if you look at the credible interval for this particular individual's attention weight, the standard deviation is substantially larger than many of the subjects, and that's nicely demonstrated by the credible interval being extremely wide. So it's not we're not really sure what they were attending to, and they weren't attending to the stimuli equally. They could have been attending to anything. Part of that is reflected here in 31's responses, where it doesn't look like it's almost like pseudo-random. It doesn't look like they understood the task. And then we can look at someone like, who's another subject? 33. 33. We go A to B to A to B to A to B to A to B. So zigzaggy, looks like irresponsiveness again. But it looks like they were just responding or weighing most of their decisions primarily on the lines, right? So stimuli that had the lines in it, or some indication of lines, they were quite sensitive to the lines. So attending much more to, not attending much more to the heights of the boxes, the tall boxes. So let's see, we imagine that 3, 5, and 7 are the shortest boxes. So let's see. 3, 5, and 7, yep. So they look all pretty short boxes, and everything else was a tall box. So they had this classification strategy where they were attending to the height of the boxes, and if it wasn't tall box, then it got put in A. And then the last subject was subject. It wanted me to look at subject 3, I think. Oh, that looks fun. Oh, that's going to be dope tomorrow. Okay. Subject 3. Take a look. Subject 3 attended much more to the lines. And so those that were category A presumably had some line, category B something else, which is similar to the stereotypical sort of classification we'd expect here, right? Except that 4 and 5 are not discriminated properly, or discriminated incorrectly. Why? Not sure. Attending the lines. Line. And then so even now I'm like doing a pseudo version of the task, right? I'm trying to create these categorizations. So it looks like all these lines are on the right side, and then these lines are on the left side. So left side and right side classification of lines, with category A being represented by right side lines. That's reflected in the subject's data. And generalization. If I'm mistaken, generalization for 31 should be terrible. Okay, good. So my intuition about what generalization represents here is that large values indicate that the pattern of responses was representative of a pattern we'd expect across other subjects. But 39 looks dreadful, but also has a lot of some variability. So it's a high generalization, but low. Okay, so 28 should look perfect. Yep, 28 is perfect. See, and they have a high generalization parameter, low variability. Well, not that low. But their pattern of responses looks really good. I think they have the highest. Just skimming these. Yeah, they have the highest too. Who else is high? 8 and 6. 6. Okay, similar pattern, right? So 4-5 distinction. 4-5 distinction, okay. So larger generalization is reflective of patterns we'd expect, given the true categorizations that we pre-specified prior to the experiment. Cool. These. But yeah, that's great. Looks like tomorrow we're going to be trying to infer some latent classes from the data. So it looks like, there's some subjects here, subject here. And we're curious, maybe these people are using different sort of rules of classification or categorization. And so we might be able to infer these latent groups from the data using some sort of mixture approach that we spoke about earlier in chapter 6, I believe. And so that's what we're going to do tomorrow. Thanks for sticking around tonight. And I look forward to tackling some of these questions tomorrow. And I'll talk to you soon.